I will talk about the possibility of using small asteroids for deflecting near-Earth asteroids. In this presentation, first, I'm going to talk about the motivation of our research, reviewing early studies and technical issues. And then our proposed mission is introduced. In particular, basic equations and variables used for optimization is introduced. And then some result of numerical simulation is shown. And in our presentation, we consider the asteroid Apophis as the target near-Earth asteroid. And finally, I will make a brief summary and talk about future works. First, let me introduce the kinetic impact missions. The several different strategies to deflect potentially hazardous asteroids is studied before. And among these, the simplest one is kinetic impactor missions. The objective of a kinetic impactor mission would be impacting the target at a sufficiently high velocity and transfer the momentum to
sorry, we have some problems of audio. Mostly related basically to the wireless.
Okay.
Just a moment, we try to solve it.
Okay.
Sorry for
I can you talk now.
Screens and it's like a simulator. You're surrounded by.
Mike, can you hear me?
Yes.
Open the control and see. Yeah.
That's almost right. It's almost doable. At least for the basic rhythm, I was always doing set up.
It's still on EDROM.
Always have this sort of problem.
なかったんですかね。今日は同じだよね。はい。
Mike, can you speak now? Mike, can you speak now? Mike, can you hear me?
Yes. May I start my presentation?
Is muted. Unmute.
Yes. Can you hear?
Can you speak?
Yes.
Yeah, I can hear you well. Can you speak again?
Yes. May I start?
It's going. My voice is going, but your voice is not coming.
I think the mic is muted.
Now it's fine. Now it's fine. Okay.
Okay.
Yes.
May I start? May I start?
Yes, Mike, you can start.
Okay. So, in this slide, I introduce the deflection mission called kinetic impact mission. The trajectory of dangerous asteroid will be changed by kinetic impact of spacecraft and nearest asteroid. And in the previous studies, the methodologies to design kinetic impactor spacecraft have been studied, both for impulsive maneuver and low thrust continuous maneuvers. And analytical expressions for the deviation due to a variation of orbital elements are derived, and optimization to compute optimal maneuvers was performed in these studies. However, the mass of the spacecraft and the resulting momentum change is very small. So large time difference between momentum change and potential Earth impact will be necessary. So to overcome this difficulty, the new approach to deflect near-Earth asteroid is proposed recently. In their studies, they use a small asteroid as a projectile asteroid to deflect larger near-Earth asteroid. In their method consists of targeting a very small asteroid to impact a larger dangerous one. And delta V is applied to small asteroid and transferred to gravity-assisted maneuver that put it on a collision course with near-Earth asteroid. However, they assume that the small asteroid is controllable. So in our study, we proposed a new approach to use small asteroid to deflect larger near-Earth asteroid. Basically, our approach is almost the same as the previous approach, but in our approach, only the small perturbation is applied to small asteroid to put it on a collision course with near-Earth asteroid, without controlling the small asteroid. And the possibility is evaluated of changing the small asteroid's orbit by application of very limited delta V impulse to put it on a collision course with near-Earth asteroid. Our proposed mission consists of 3 phases. In the first phase, the spacecraft is launched and departs from the Earth. And in the second phase, the first kinetic impact between spacecraft and small asteroid occurred. And then in the third phase, the second impact between small asteroid and near-Earth asteroid is occurred. And finally, the trajectory of near-Earth asteroid will be deviate from its original dangerous one. And now I show you the basic equations. In the second phase, we can see that the velocity vector before and after collision can be related like this for both spacecraft and asteroid. These relations are used in the next slide. And from the conservation law, we can obtain these equations. And here, all the impact are assumed to be perfectly illustrated. So, and we set the gamma as a mass ratio between small asteroid and spacecraft. And we can obtain the final expression for delta V for spacecraft. And by using this relation and this relation, we can obtain the total delta V shown here. In this expression, the delta V, the first term is determined by solving Lambert's problem for phase 1, and the second term is determined by solving Lambert's problem for phase 2. And gamma is the mass ratio of small asteroid and spacecraft, and assumed to be very large. And now I introduce the variables used for optimization. And this figure shows the first phase. The blue trajectory is the Earth orbit, and black orbit is the original small asteroid orbit. And green line shows the first Lambert transfer orbit. To obtain the first Lambert transfer orbit, the true anomaly for Earth departure and arrival of asteroid is considered as a variable. And also we consider the revolution number and time of flight as a variable, optimization variables. And this figure shows the second phase. The the red trajectory shows the trajectory of near-Earth asteroid, and the yellow one shows the second dumbbell transfer orbit from small asteroid to near-Earth asteroid. And in this second phase, the true anomaly of the departure of the small asteroid and arrival of near-Earth asteroid is considered as optimization variables, and revolution number and time of flight for this second dumbbell transfer orbit is also considered as optimization variables. And to design the whole mission, we combined both phases, and these 7 variables are considered as optimization variables. And optimal combination of the variables are sought among the asteroid, which is selected from the near-Earth class with order of 200 to 3,000 tons. And this table shows the orbital elements of Apophis and asteroid used in the later simulations. Here we consider the 1480 asteroids as a candidate asteroid shown in this figure. And this first figure shows the relation between total delta V and mass ratio. We can see that the horizontal axis shows the mass ratio of spacecraft and asteroid, and vertical axis shows the total delta V. And we can see that the total delta V is almost proportional to mass ratio, and we fix the candidate asteroid in this yellow region. And this second figure shows the relation between total delta V and the number of revolution. And each color shows a different number of revolution. And we find that the minimum delta V is almost the same for each revolution. So we fix the number of revolution at 0 in the later simulation. And this is the tables which shows the delta V's for each phases. And we can see that the total delta V is very small for some asteroids. And we can also find that the delta V asteroid in phase 2 is in the almost same order. So this is the characteristics of our mission. The delta V asteroid is the dominant factor. This is the example of optimal transfer trajectory from using the asteroid 20 to EM40. The blue line shows the Earth trajectory, and black line shows the small asteroid's trajectory, and the red line shows an Apophis trajectory. And in this figure, the green and pink line shows the transfer trajectory from Earth to small asteroid and small asteroid to near-Earth asteroid. And we can see that the second dumbbell trajectory described in pink line is almost the same as the original small asteroid's trajectory. This figure shows the delta V necessary for second phase and the time of flight. The horizontal axis shows the time of flight, and vertical axis shows the delta V for second phase. And I will show you the counter plot for each time of flight. for these 5 regions. This is the result for the 120 days of time of flight. The left figure shows the counter plot of total delta V. In the left figure, the vertical and horizontal axis shows the mean anomaly of asteroid and near-Earth asteroid apophyse. And red point is the minimum point of delta V. And the right figure is corresponding to the trajectory for minimum delta V. And please see the left figure and red point in this figure. And by changing the time of flight, the red point converges to some point. But by changing the time of flight, the red point moves parallel to the horizontal axis, which means the collision point does not change by increasing the time of flight. And I go back this slide. And please see the right figure. In this figure, the red point is the optimal collision point, and black point is the optimal departure point for this time of flight. And by increasing the time of flight, the departure point move along the small asteroid's trajectory, and the collision point described in red point does not change by increasing the time of flight. So we can see that the optimal collision point is always at intersection point of near-Earth asteroid and small asteroid. And optimal departure point converges as time of flight goes to infinity. And if the time of flight is too long, the trajectory, Lambert trajectory deviates from the original small asteroid's trajectory, and the delta V necessarily become rapidly increased for larger time of flight. And this is a summary of the simulation. The feasibility of the mission depends on the delta V for phase 2. And the optimal collision point of phase 2 is at the minimal orbital intersection distance. And optimal delta V asteroid is almost proportional to the closest distance between small asteroid and any nearest asteroid, which can be understood from the proximity motion equations. And this is the conclusion. It was found that the very small delta V may be required to transfer small asteroid to the trajectory followed by collision of this asteroid with the hazardous object when it has very small minimal orbit intersection distance. The proposed method allows to change velocity of dangerous object by the value of unachievable by any other contemporary technologies. For practical implementation of the proposed approach, the candidate small asteroid in need will be found among the catalog asteroid in consideration of ephemeris. Thank you.